Hi, I'm Richard Connor, and I'm presenting this work, which is joint with myself and Alan Dearle, now both at the University of St Andrews in Scotland. And the title is Sampled Angles in High Dimensional. So here's an outline of what we've done in this paper. It's a matter of folklore. We're told that in a high dimensional vector space, sampled vectors are nearly always orthogonal. Um, Folklore is great, but we do want to quantify that effect, which has been done by other people. But this seems like somehow an effect that might be very useful. Usually we're used to things getting harder as dimensions become higher, and maybe here's an attribute of a high dimensional space which we might be able to use to affect. Of course, first, we're not interested primarily in high dimensional vector spaces, so we first have reinterpreted this folklore into general metric spaces, and we've quantified the useful effect which remains in general metric spaces, and we show how to predict, based on these angles, when the intersection of two hyperspheres is likely to be empty. And this is something which is very useful in the context of querying a finite metric space. Things are not lovely. The theoretical property stands only in unbounded high dimensional vector spaces. We obviously are searching usually in bounded object spaces, which do have some quite different properties. So we show these properties. We show that there's a concept of outlierness that we need to take into account before we can observe the angle distributions. But we do have some hold on that, and we show some first results of this work by applying angular predictions based on, but not the same as, the high dimensional vector space model to a laser algorithm. And we have some quite promising and quite exciting results. Okay, so let's revisit the folklore, which really does seem to be folklore. But any two randomly selected vectors are nearly always orthogonal in a high dimensional vector space. So some work relatively recently has quantified this, so now we're a bit more scientific about it. There is the probability density function for the angle theta, which is the angle between two randomly sampled vectors from a vector space. So a complex formula, but many of you will recognize most of the left-hand side of that is just based on the volume of a hypersphere in p dimensions. So this is in p-dimensional space, this formula. And you'll see that the main, not the main, that stuff is all effectively a constant, more or less, with respect to the angle, and therefore the main effect is on the right-hand side of the dot. You'll see sine theta to the power of p minus 2. So the probability density function is directly proportional to the p minus 2th power of sine of theta. So on the right-hand side, we can see that as p gets greater, so this graph of this probability density function in 4 different dimensions in 2, 10, 20, and 30. And the higher the dimension, the more collected around the center being pi by 2 or 90 degrees, the angle between the vector. You can see that in even 30 dimensions, and nowadays we're looking at creating many more than 30 dimensions, the values of the density function at the outlier quarter, say, of this graph are effectively zero. Thing I'm not going to talk about, but is in the paper, is that these high powers of sine graphs are spookily close to a normal distribution function in actual fact. And so if you know the normal distribution function, these really are effectively zeros whenever this gets close to the x-axis. So that's nice. But in this conference in particular, we're not really just interested in vector spaces. We're not really at all interested in vector spaces, but we're interested in high-dimensional general metric spaces. So is there a result from there that we can take into high-dimensional metric spaces? Well, one good thing we have, we can't measure the angle between any two objects like we can with two vectors, but we do always have a finite 3 embedding in two-dimensional Euclidean space for any metric space. Simple corollary of the triangle inequality property. If we can always form a triangle from the distances among three objects, then we can measure the angles. Is the mean angle 90 degrees? Clearly it's not. Clearly the mean angle is 60 degrees if we sample three objects randomly within the space and pick one of the angles to measure. So if we just think about Euclidean space, which is essentially isomorphic to a vector space that we had earlier, if we pick randomly three objects x, y, and z, then we could consider the vectors yx and yz. And are these orthogonal? Well, no, they can't be, because if they were, then also we'd have zy and zy, and that should of course say zy and zx, and xy and xz would also be orthogonal, so they can't all be orthogonal. Otherwise, we'd have 270 degrees in the triangle. So something different's happening here, and what's different is that when we're sampling vectors from the origin onto a unit hypersphere, and we'd have lost that control in the. But luckily, we do have the original property in this way. If we fix x and y, so we can sample them, but we're going to fix them, and then we're going to sample z within a fixed radius of t. This is now equivalent in a Euclidean space, essentially, to picking the point y and shifting the axes by translation so that y has become the origin, and then picking z, sampling z on the surface of a unit hypersphere. So if we do this, then we do get the same distribution of angles, and we get this the same property of the angles in higher dimensions being clustered tightly around 90 degrees or pi by 2. And this is becoming important because if we sample z randomly, then the distribution of angles is centered around 60 degrees. If we sample z on that hypersphere, then it's 90 degrees. And what we're going to show is, in actual fact, sampling z on the hypersphere is not very different from sampling z within the hypersphere, because in high dimensions, most objects within the hypersphere are going to be close to the edge of the hypersphere anyway. So we're going to get a very similar effect, actually with a slightly different power of sign. And this is why we care, and this is why we care deeply. So here's a picture that you'll see in many papers about metric search, in any textbook or any survey paper about metric search. Is the bottom right hand corner. We have a finite universe within an infinite metric space. The finite set is called S, and we have, at pre-processing time, sampled a point P, which is the pivot point. We've divided S into all those objects which are within a distance m of P and which are outside the distance m of P. So we've called those subsets S in and S out. And at query time, we're going to measure the distance PQ. And in the classic pivoting mechanism, if the distance PQ, for example, is greater than m plus t, then the intersection of these hyperspheres is empty, and we don't need to search S in for any solutions to Q. No solution to Q can be within the set S in. So that's good. About these angles, why do we care? Well, you can see the green shaded area, which we'll come back to, is defined by an angle theta between PQ and any solution S, which is within distance Q distance t of q. And what we have, if that angle theta is tightly distributed around 90 degrees, pi by 2, then the intersection which exists in the infinite domain is very likely to be empty within the finite domain. And never mind very likely, we need to be able to quantify that and assign a probability to a member of the finite set that we're searching being in that intersection. Or we can't measure the intersection, but we can measure that green shaded area to volume of the hypersphere. And if it's very, very likely that there'll be no elements of the finite set in that green area, then we can exclude the set Sn, even though the triangle inequality doesn't prove that the intersection is empty. So, as you will find the details in the text of the paper, I'm not going to try and present them here. Fairly straightforward mathematically, in actual fact. We can quantify not the probability of the intersection being empty, but we can quantify the probability of a value from the finite set, assuming it's evenly distributed. We're still really talking about Euclidean domains here. As this, so we've got a probability density function h, and h is the probability density of a value from within that right-hand hypersphere, the one surrounding q, bounded by t, of having that displacement x along the line pq. And as x varies from 0 to 2t, we can see the probability, again, these are the same dimensions as before, increasing rapidly for the higher dimensions near pi by 2. And quantifying this, in actual fact, in a 30-dimensional space, if we have this situation, which is quite feasible to achieve with the distances between p and q based on m and t, then the probability of an element of the finite set being in that domain is around 1,000th in actual fact. So we have a very good chance in only 30 dimensions of being able to safely exclude that S in an approximate search mechanism, and we will only lose less than 1 in 1,000, sorry, more, around 1 in 1,000 of the correct solutions to the query by discarding S in this situation. So, as is often the case, the theory is beautiful. The theory is measurable and correct for high-dimensional Euclidean spaces, and we've verified that experimentally, and we show results for that. But it only holds in pure terms for unbounded Euclidean spaces, and unfortunately we tend to query bounded spaces. So when we have a high-dimensional Euclidean space, usually that's some set of attributes which have been modeled, distributions along each dimension, and of course the dimensions have lower and upper bounds. So this theory only holds if the whole of the query hypersphere, that is the whole of the space in the unbounded and in the infinite domain which surrounds the query, actually is contained within the finite bounds of the data space, and that doesn't happen in higher dimensions. So for example, even in only 20 dimensions, because as the dimensionality increases, the volume of a hypersphere becomes tiny, infinitesimally small quite quickly. The nearest neighbor distances become huge because you've got to have a really, really big radius on your query hypersphere before you have any elements of the finite set inside it. So 1/1,000,000th of the volume of unit hypercube in 20 dimensions has a radius of 0.6. So 1/1,000,000th of the space, which is usually around, depending how big your data is, but you want to query at least that much of the space. Even with 1/1,000,000th of the space, necessarily a substantial part of the potential solution space is sitting outside the data space. So we need to adapt the theory to accept this. So here's verification experimentally of the theoretical results. In these experiments, we're using generated Euclidean datasets and in 10, 20, and 30 dimensions. And in each case, we're making random selections of 2 points, x and y, in our previous term. And we're then selecting a third point within a fixed radius of y. So we're measuring the angle xyz. In each case, you see the left-hand curve, the brown histograms, are plotting the angles where the choice of x is unconstrained. That's randomly selected from the whole data set. And in the right-hand histograms, so the blue histograms, we're then constraining the distance within which we're sampling z from y to be such that the whole hypersphere is contained within the bounds of the data which is generated. So this data is generated in the unit hypercube in all cases, and we're showing exactly the peaks of these graphs, 60 degrees in the left-hand histogram and 90 degrees in the right-hand histogram. So this is a perfect result, in actual fact, exactly what the theoretical model predicts, which is always nice to confirm. And however, as previously mentioned, that is an unrealistic situation. So we've constructed another synthetic experiment where we again generated data within the unit hypercube. And instead of randomly selecting the center, the query point, when we're measuring the angles, we slid it from one vertex to the opposite vertex. So at the left and right of both these graphs, we're seeing cases where the center, the query vertex is close to the boundary of the data space, and in the center, the query is well central in the middle of the data space. And you won't be able to read the scales in these graphs, but on the left-hand side, we're measuring the angle. Again, this is the mean angle for all potential solutions to the query. And you can see when the query is towards the center of the space in the middle of the data, we hit exactly this 90-degree prediction. But when it gets towards the outer edges, closer to the outside of the data space, then this angle drops as far as 60 degrees, or in fact slightly less, but that's another point. In any case, we're not going to believe this mechanism works if we don't try it on some convincing non-generated, non-synthetic data. So we're using these 4 data sets. They're all fairly serious data sets. Perhaps real world is an overclaim, but it's commonly used as such in academia. These all have 1 million data elements in them. They're of various different complexities. Deliberately, the spectrum has been chosen to go from what is more or less a normal Euclidean space through to more and more restrictions in spaces that are not Euclidean at all. Because of course the theory of this only works for uniformly distributed Euclidean spaces. So this is 2 of the 4 sets, the other graphs are in the paper, to see if we can re-establish this correlation between outlierness and the mean angle. And there are interesting correlations here. They clearly are very clearly correlated, even if we don't fully understand them. So we've measured outlierness using a mechanism in the paper. It's not a very good measure of outlierness. Point here is we're only using distances now. We're not using the coordinate systems in any of these spaces. They don't even all have coordinate systems. But we're just back to the sort of black box metric approach. We're only going to use distances to just try and apply this result. So we do have a way of mapping weakly from outlierness to the mean angle we're expecting. So we will apply this now to actual query experiment. And our experiment is a very, very simple one. So we think that this technique can be used in much more sophisticated scenarios, but we're just trying to prove the concept of this angle distribution and show that it can be used to make exclusions relatively safely in certain circumstances. So we use the variant of LISA. LISA is a very well-known mechanism. The variant of this is based exactly on that picture of the two hyperspheres. Instead, we are essentially calculating the picture, including the angles. We're working out the angle theta and seeing if the angle theta is lying outside the most likely range for that angle to be, according to the probability density function of the angles. So we're measuring the outlierness from the distance to each reference point. We're trying to find the most likely angle for the center of these angles to be for the square solutions, and we're excluding based on some plus or minus tolerance around that angle. So here's the results, and the results are actually excitingly good, I would have said. On the left-hand side, essentially left to right on these scales, we are increasing the accuracy, so decreasing the tolerance, if you like. We're allowing a less wide band either side before we allow the exclusion to happen. So in the far left of all these scales, we're allowing exclusion where there's really quite a lot of overlap between the two hyperspheres. And on the right-hand side, the far right points, which corresponds by 2, essentially there is no overlap at all. So that's degrading to a standard LISA mechanism. So of course we have perfect recall on the right-hand side of the graph, but we can go a long way to the left before we get any drop in recall at all. Precision is perfect here. We can't get any false positive results. We can just fail to find correct results. We get false negatives. So that's good. We can go plus or minus 0.6 radians. That's quite a wide sweep without losing any correct results at all, essentially, for all 4 of these sets. And the higher dimensional sets, we can go further, which again fits exactly with our observation of the higher the dimension, the narrower this distribution of angles becomes. And the right-hand side of these graphs shows the cost. And you can see looking at the 2 graphs, the trade-off between the cost and the recall. So I think that's all about I can say during this presentation. Of course, the full details are in the paper. We're doing more work on it, and we've got some more promising results. This very much is the moment. We're just presenting the proof of concept. But we're quite excited. The very unusual thing here is that the higher dimensionality gets, the more traction we have with this mechanism. Usually, of course, traction disappears as dimensionality becomes very high. So we're hoping we'll eventually get some really good scalable ways of querying these very high dimensional data sets using approximate, but a different approach to approximate search. There's lots more things still to do. We think we can get much better analysis on the angle spread for query solutions based on the pivot characteristics as well. We're just looking at one fairly superficial attribute of the query at the moment and doing fairly well with that. We think we can do much better if we have some more information, which is available at query time quite cheaply. We've only shown one variant of pivoting using a single pivot, and using LISA, we think there's a lot of potential using hyperplane exclusion, and in particular in spaces of the 4-point property. We think we have a much better view of what these angles can do to help us. And we generally want to understand the effects of local density and local intrinsic dimensionality far better in some of these high dimensional spaces, but we're not the only people who would like to understand these better. So, thank you very much. Thank you for listening, assuming you have, of course we can't tell. If you have any questions, feel free to contact us by email, or indeed if we happen to meet at some point.